Thanks a lot for having me here. It's a great pleasure to be in Vienna again. So this is already my second time and not the last time. Even before the end of the summer, I'll be here at the end of July for ICML. I'll talk about an algorithm that everybody knows, SGD. However, it turns out people typically think of SGD as a serial algorithm, and we know that, let's say, in the smooth non-convex regime, it's optimal in a certain sense, the matching lower bound, but in the recent decade, people are interested in solving very huge problems, and for these huge problems, you need many machines. You need to work in a distributed environment, in parallel environment, and maybe these machines are heterogeneous, so they may have different speeds, different communication speeds, different compute speeds, and so on, and it's not clear at all what the right version of SGD is in those regimes. So this is really what the story is about. So I created this tweet a couple of days ago. It already has 733 likes. Please like this. I was told by Radu that this is appreciated. Okay. So this is my team, and all of these things that I'm going to talk about, the main author is Sasha Turin, and some co-authors who are on this photo are Ivan Ilin and Kaya Grunkowska. So the introduction of this is a very basic description of a basic problem that everybody knows. That's finite sum minimization. You want to minimize the average of a bunch of functions. Each function is the expectation over some local data. And these distributions can, in general, be heterogeneous, and you have n machines. And the main difficulty here in this talk is that these machines are heterogeneous. So machine I will take tau I seconds to compute one stochastic gradient. And these tau i's can be arbitrarily different. There's possible heterogeneity coming from the distributions delta or di. And at the same time, you may have communication heterogeneity. So when the machines communicate, and you can imagine they communicate through some server, let's say, it could be peer-to-peer communication, this takes some amount of time as well. However, in the main part of this talk, these theta i's will be just zero. There won't be any communication speeds. I'll talk about the version of the algorithm where only computation times are different. So that's the key, and what we want to find is approximately stationary point because we'll be working in the smooth non-convex regime mostly. There are some results in convex regime as well, but I will just hint at those. So the way you should imagine this is that you have a server. The server doesn't have any data. The clients, the nodes, the machines have data. And what's going on is that the server sends the model to some machines. So it could be at the same time to all, could be asynchronously. I'm not trying to say this is going to be analysis of synchronous algorithms. In fact, there'll be some asynchronicity in these algorithms. And the workers compute stochastic gradients. The workers are machines that compute stochastic gradient. They will not be updating the model. And then maybe they compute one, maybe they compute several. After this, they send this to the server again. The server does something with this, or maybe waits for a few of them and then updates the model, or maybe does it synchronously and so on. So it works like this. So these arrows would correspond to communication, and here is where the computation happens. And the server is the entity that updates the X, the iterate. So there are three types of heterogeneity here, and tackling all of them at the same time turns out to be difficult. We don't know how to really do that yet. Data heterogeneity, so these data distributions could be arbitrarily heterogeneous. This is not really the main part of this talk because there's a lot known about this already. However, the key part is the compute heterogeneity and then also communication heterogeneity. Okay, so what kind of assumptions do we have? So obviously we're going to assume the function is at least lower bounded so that we know there would be a stationary point and some Lipschitzness, and the stochastic gradients have all bounded variance. So these are classical assumptions. So these are, I say, typical assumptions because in some results we work with a finite sum regime, and then we don't need this kind of a strong assumption. We can work with weaker assumptions. Sometimes we have convexity, but this is typically what we're going to see here. All right, so we have written 4 papers in the last year or so on this topic, and these turn out to be all optimal algorithms with matching lower bounds, and there haven't been optimal algorithms in this setting yet. So the first one was from a year ago, and there are 3 algorithms there: Rennala SGD, Malenia SGD, and accelerated Rennala SGD. I don't know whether anybody recognizes these names. We'll talk about this a little bit later. And so Rennala SGD turns out to be optimal parallel SGD under computation heterogeneity when data is homogeneous. So we could figure out the computation heterogeneity part, but we had to assume data homogeneity. Malenia SGD is optimal parallel SGD also when the data is heterogeneous. So the algorithm is slightly different. And accelerated Rennala SGD is also optimal in the convex setting, but then in the data homogeneous regime, but in compute heterogeneous regime. So that was the first work. Then in the second work, what we wanted to see is, can we throw in some communication times here? Because people are interested in communication complexity, in compressing communication, and so on and so forth, in local training phenomena. And it turns out that we could. So we came up with this algorithm called shadow SGD, and it turns out to be optimal under arbitrary communication costs and computation costs. However, we had to assume data homogeneity in that case. So we got two types of heterogeneity, but not the third one. So we don't know how to do that. In this third paper, this is very recent, we have yet another optimal algorithm. So here what we do, we assume more structure. We assume that these local data sets are finite. So we have finite sum. We don't have to then assume bounded variance on the gradients. We can do something stronger. We can throw in some variance reduction techniques in there, and then we get optimal algorithm under arbitrary computation heterogeneity, no communication cost, and data is homogeneous. And this optimality holds if you have enough data more than the number of machines squared. And finally, we extended these results to the decentralized regime. So this is where the names of the algorithms come from. I'm not responsible for this. Somebody else, you can guess who on the team is, and he plays a lot of games, and all of these are some characters from some games. Okay, I think we run out of the names of girlfriends of people on my team, I guess, because we have these algorithms called Diana and I don't know what. Okay, of team members. All right. So these are the algorithms, and you can see they're kind of grouped into 4 rows. Those are the 4 papers, and this is maybe a very high-level way of thinking of this. You can see, for instance, here that only this last paper deals with decentralized setup. You can see which ones are optimal, which ones are not. You can see that in this one case, we deal with the convex setup, everything else is non-convex, and so on and so forth. So that's a summary. I will not really talk about this too much. So let's start with Rennala SGD. My goal is just to explain that algorithm, what it does. So you'll see it's a very simple algorithm. Let's start with the first approach to how you might want to use n parallel machines to minimize this function to find an approximately stationary point. So this is a kind of strawman algorithm where you just say the fastest guy does all the work and nobody else works, everybody has vacation. So this is what you would do. Obviously, it doesn't look like it's the best thing you could do. On the other hand, if these 2 other workers are very, very slow, maybe that's the optimal thing to do. There might be a regime where this is the best thing to do. In any team, if you have sufficiently inefficient workers, maybe they shouldn't contribute to the work, right? So we know that. So minimax SGD, or fair minimax SGD, which is another strawman kind of an algorithm, would be saying everybody contributes with 1 stochastic gradient, and you wait for everybody to do their job, then you average and continue. Looks reasonable, but it also doesn't look super efficient because what if the slowest guy is so slow that you wait way too long? Maybe it makes sense to drop that person, for instance. Anyway, this is an algorithm one can run. So it is actually synchronous minimax SGD with minimax size equal to the number of workers. Yes, Steve? So we have analysis when we know these things, but we also, the algorithm doesn't need to know these tau's, and we have analysis of those things too. We even have analysis where the tau's change, but I think it's good to assume that, let's say we know this, but the algorithm works without the knowledge. And then the third approach might be, okay, we don't want to be in a situation like this or like this, so let's make use of everybody maximally. So that's the greediest possible approach. It's called asynchronous SGD. So one way to think of this, the algorithmic idea behind this is everybody is a slave, which means they have no free time. They just keep working, and they're useful also. So you don't think that anybody is not useful even if they're slow. So that means as soon as you get a stochastic gradient from someone, so from the fastest one, you update the iterate. And then you get another one from this guy, from the last worker, and you update the iterate. Right? And as soon as somebody finishes, you ask that worker to compute stochastic gradient at the latest iterate. So now you have this very strange dynamics here where maybe some potentially very old gradients get introduced into the update a year later, let's say, and that looks doesn't look optimal. Right? It looks like maybe that's not the right thing to do. Anyway, this is asynchronous SGD, and it became very famous due to Steve and his co-authors. And so there's this algorithm, Hogwild, very famous, got Test of Time Award in 2020 for some reason. 2020 is also when it has the highest number of citations. I don't know whether that's any coincidence or not. So it was very influential work. I visited Steve at about the time, and I kind of refused to collaborate on a follow-up paper, which it's a huge mistake that I made. I should have done that, but I didn't know at that time what actually how amazing that work would be, how influential it would be. All right, so our interest in this topic got reignited about a year ago when these two really beautiful papers came out, almost at the same time. You can see the dates, just one day apart on arXiv. So one by Kostya Mishenka and his co-authors in Paris, and the other one by Anastasia Koloskova and her co-authors at EPFL. So what they basically done, they looked at asynchronous SGD again, try to reanalyze it from different point of view and come up with some solid complexity analysis. So before these analyses depend on delays, which you might know what they are. So these delays, I would say, I'm not going to get into this too much, but these delays in my mind, they just hide what's going on. And this is one of the reasons why I didn't like these kinds of analyses, because you don't have this honest complexity which tells you what was really happening. But these authors managed to circumvent this and showed that under some assumptions, asynchronous SGD can actually beat minimax SGD. So this was the starting point for us, and this is the first paper on SGD, where we looked at asynchronous SGD again, and the idea that we've got was this. If some workers are so slow that intuitively they shouldn't contribute, then they shouldn't contribute. So that was the first idea. And the second idea was maybe it doesn't make sense for the algorithm to be fully asynchronous. Maybe you should have some amount of synchronicity, some amount of asynchronicity, and maybe that's going to be optimal. So what our algorithm actually is, it is a synchronous mini-batch SGD method with a certain mini-batch size. However, that mini-batch is collected in an asynchronous fashion. So basically, there is a mini-batch size, in this case, would be sigma squared divided by epsilon, where sigma squared is the variance bound. Epsilon is the accuracy you want to achieve. And you just wait, you ask everybody, compute as many stochastic gradients as you can at xk, and just keep going. As soon as you get mini-batch size of size sigma squared over epsilon, you say stop, and the server updates and the x, and then asks this again. So that's really what the algorithm is. Okay, so semi-synchronous, semi-asynchronous, yes? Yeah, basically those are not useful. And if you knew these compute times a priori, you could just tell them you're not part of the team. You cannot help. You make things worse. Yeah, they're toast. They won't contribute. On the other hand, the algorithm has analysis and it works without the knowledge of these compute times. So if these compute times change because some worker was just busy with some other jobs and maybe they become faster later, then they contributed some other iteration. So that's all right. So that's really what the algorithm is. I don't have to do a formal description. So that was all that was going on. So then we proved this upper bound for the algorithm, but now it's in seconds. It's not in iterations, because we assume that, let's say, the aggregation, the update step is instantaneous, and we assume that the computation times are the only things that really matters. So this is in seconds. And you can see there's some sort of a harmonic mean of the m fastest compute times, and you optimize over the n. So let's look at this. So we have n machines, and we only use m machines in the end. So once you solve this optimization problem here, and we don't have to solve it, this is somehow automatically done by the algorithm, That's the cutoff after which all the other workers above this minimizing and M would just not contribute at all. Then tau i's are the compute times. These are the Lifshitz constants. This is initial suboptimality, and so on and so forth. So this is the upper bound. I'll pause here in case there are any questions, and I'll compare this to some other upper bounds for these competing algorithms. So M is a number of workers between 1 and n. If M was 1, if you solve this minimization problem and M was 1, then you would get the hero SGD algorithm, and that would be the optimal algorithm, and everybody else should just have vacation. If M is n, then everybody contributes. If M is, I don't know, 3, only the 3 fastest contribute. That's what will happen. It just comes from analysis. So one iteration is this mini batch with mini batch size sigma square over epsilon, max of that than 1. You have to have at least 1. And it would take the same amount of time if these compute times tau i's were constant throughout. They were not living in this world where they may change. So, and this theorem applies to that case. So then every iteration takes exactly the same amount of time. And this would be just the product of the iteration complexity of mini-batch SGD, synchronous mini-batch SGD, and that time. So it's not hard to prove this. So this is quite easy to prove because you already have one part of this. You just have to figure out what is the fastest way to collect that mini-batch. Okay, that's all. So the surprising thing is this lower bound, and the lower bound matches the upper bound. So it turns out that algorithm is optimal. So this is the first optimal parallel SGD method. So now, looking a little bit behind the scenes, what's going on, typically, traditionally, SGD is analyzed, or first order methods are analyzed using this classical Oracle protocol, where you have some function class, Oracle class, algorithm class. In this case, there's some distribution because we work with SGD. So typically, this would be just stochastic gradient. And then the complexity measure is this. So you look at the best algorithm from the algorithm class and the worst function from the function class, and so on. And the point is that you count the number of iterations until you get epsilon stationary point. However, counting the number of iterations doesn't make sense in the parallel regime where things can happen asynchronously and at different times. So we could not use this. And this was maybe one of the reasons why people didn't have proper lower bounds and didn't know what exactly to do with the upper bounds and so on. So we had to rethink this and think about what to do instead. So this is very natural for sequential methods where the number of iterations actually corresponds to time. You just multiply by maybe cos of one iteration. However, for parallel methods, that's not the case. And we're thinking of a new oracle which keeps track of time. And that's the orange T's. This is the time. So I'm not going to go into this in too much detail. But the point is that the oracle actually behaves as a normal worker who is aware of at what time it was asked to compute stochastic gradient, how much it takes it, and then it lets know, it outputs the new time, and so on. So the time is being tracked as opposed to the iterations. And instead of the classical complexity, we have this complexity with these changes. So we have time, and we look at the time now instead of iterations. The time it takes for us to solve the problem. That's what's going on. And we cannot use just this one oracle. We have to use multiple of these oracles for each worker. It's additional complication. So now here's a summary. We have the upper bound and the matching lower bound, and the previous algorithms, two of those, I didn't put in the hero SGD there, have these bounds. So these are the very nice papers, beautiful papers by Koloskova, co-authors, and Mishenkan co-authors, where they have the harmonic mean. We also have the harmonic mean, but they work with every worker. So that's the weakness of asynchronous SGD, that it's unable to realize that some workers just should not contribute. So one way you can think of our result is that this is something very similar to what they have, except you learn that you should only work with a few first fastest workers and not beyond. Okay? Then it would be basically the same thing. And the mini-batch SGD, you can see works not with the harmonic mean of the compute times, but the worst one, the largest compute time, because you have to wait for the slowest, and so on and so forth. So this is the main result I really wanted to talk about. Let's pause here again. 5 minutes, all right? Yes. There are constants, yeah. There is this constant 96 or whatever. So up to absolute universal constant. So they don't match in. I don't know. I don't have an answer. Yeah, the order matches. So these results are not as beautiful as the results that Ben was talking about, where everything matches perfectly and so on. We're not there. So when you run the algorithm, so here with 10,000 workers, of course, we didn't have 10,000 machines. We just simulated this. And this is in some regime where we also simulated the compute time. Square root of I is the compute time for worker I. Okay, this is just imaginary. This is not a real machine. But you can see that in this case, Rennala SGD is doing very well compared to asynchronous SGD, and mini-batch SGD doesn't seem to be on the plot, and I don't know why right now. All right. So there are some extensions. In the same paper, we looked at the case where the data can also be heterogeneous, which is more complicated, because now you cannot ignore any worker, because they contain some part of the problem description, and you are unable to solve the problem without their input. So the algorithm is slightly different. I'm not going to describe it. It's almost the same thing. You just make sure that everybody contributes at least once. It's the first order approximation of what the algorithm is. And then the result is different, but we have a matching lower bound. So you will have arithmetic mean now of the compute times something. That something will be 0 if there's no stochasticity. And you also depend on the slowest worker. And you have to, because everybody has to contribute. And the way, yes, Yura? It's not strange because we just assumed it. so the analysis, this is like the largest of the Lipschitz constants. So we didn't do that kind of fine analysis where we'd say everybody has their own and what is the dependence? Is it on average or whatever? We didn't do that. So it's rough in that respect. And if you look at, let's say, mini-batch SGD, you would see that the slowest time is multiplied by both of these. But in these results, the average is, instead of the slowest time, is multiplied by the second part of this. That's the difference. We look also at the convex case. Yeah? This is simple average, yes. Reason. So then we look at the convex case too, but here we had to assume that the function is Lipschitz and the gradient is Lipschitz, and we assume there is a bound on the distance to the solution. So these constants Lm and R appear. We do have a matching lower bound. This is the upper bound. The complexity is different, and it is better than these previous upper bounds. Okay, so this is really the end of it. I don't know how much more time I have. I have some extensions, but those are optional. I have a few more minutes. So I'll pause here in case there are any questions, and if not, then I still have time. I'll just hint at some extensions. Yes? Right, so there are some kind of modifications of classical examples. So there's not huge innovation there. The innovation is in how to work with these new protocols, how to keep track of all of them. No, so in this case, for Rennala SGD, everybody computes stochastic gradient with the variance sigma squared. That's the oracle we have there. And as soon as they do, send it to the server. Yes. However, and this is an excellent question for one of these extensions, for shadow hard SGD. So for shadow hard SGD, this is the algorithm. And I don't have the arrows which say what is what, but BI is the mini batch size now. So for shadow hard SGD, the communication cost also matters. And the optimal algorithm actually does the following. Every client or worker computes a mini batch of these stochastic gradients, and the mini batch size is BI. Then they compress the mini batch and send it to the server, and they do it MI times. And then you have to do some kind of weighted combination of these compressed things, and that turns out to be the optimal thing to do. Yeah. Yeah, there's a lot of things that can be, there's a lot of room to come up with maybe alternative ways of getting optimal algorithms and so on. I'm completely with you on this. So this would be the optimal algorithm with proper WIs and compressors and so on in the presence of data homogeneity. We cannot do it right now for data heterogeneous regime, but arbitrary compute and communication heterogeneity. So this algorithm. This is how it looks like. I will not really talk about it. The complexity is somehow implicit. It depends on something that we call equilibrium time. We don't have a closed form expression for it, but we have a lower bound, which is exactly the same thing, and they match. And here, I think the most important thing to look at, because this is just very hard to kind of interpret, is this. So these are just some examples when sigma squared over epsilon is 1,000 or a million, and you would see how these previous algorithms are, let's say, 100 times, 10 times, or 10,000 times slower than our algorithm in those regimes. So we just plugged the numbers into the bounds. I think I'll stop here. Yes? Unchanged. Oh, it's different now? Yes, we didn't think of that regime. But if the upper bound is the same, then we don't care who these workers are. The algorithm works even if they drop out. We just keep asking workers to compute stochastic gradients. Yes. Well, it may happen, but it's not. So if the optimal M for solving this thing happens to be, okay, N, it might be the case that that's exactly what's happening. That the slowest worker computes just one stochastic gradient, the fastest computes how many it wants in order to match the slowest worker, but it's a coincidence. So this depends on all of these numbers in here. It may happen, but in general, it will not happen. Well, yeah, because the individual stochastic gradients have the same variance, and then when you mini batch, of course, the variance of the mini batch goes down, but it's fine. It's okay. There's another problem there. Thank you very much.